All right, good morning, class, and welcome to this lesson on tension. Today we are going to be able to solve for tension given various pulley situations and situations in which an object is hanging from angled wires. So let's just get started here. Let's draw a object hanging from a pulley. This object is hanging from a pulley, and this object pulls down with a force of 10 newtons. This object pulls down with a force of 10 newtons. What force do we have to apply here? What force do we have to apply on this wire to get this to just start moving? To get this to just start moving. And if you look at the situation, the tension in the rope is going to be the same throughout. The tension in the rope is going to be the same throughout. Therefore, if this object is pulling with 10 newtons, free body diagram, gravity is pulling it down, tension is going to be equal and opposite. The force required to pull this object up is going to be 10 newtons. Okay? Not too bad, right? Well, it gets a little more complicated than that. So, let's draw, we're going to have a ceiling here. So let's draw another pulley with another box, and the box is also going to pull down with 10 newtons. Well, this pulley and this box are attached. So whenever we pull up on this rope, it's going to pull the pulley and the box up. And just for general reference, for all these problems, just assume the pulley and the string are massless or have no mass. Okay, so that'll make this a little bit easier because of that. Okay, so we have this situation here where the pulley and the box are moving together with the string. So what is the force required to get this moving? And I suggest if you want to pause it right now, try and figure it out, and then wait for the answer. So here we go. We are going to treat this as all one system. And if we look at this as one system here, we have a force pulling up on the left, we have a force pulling up on the right. So if we drew a free body diagram, we would have gravity pulling it down, and we would have tension pulling it up and tension pulling it up. So these two are going to be both equal, so that means 2T equals mg, or T equals 10, 2T equals 10, and T equals 5 newtons. So you notice from this problem right here, because we have it's one wire, but it's attached here and it's going to be held here, attached here and held here, we only have to apply a force of 5 newtons to lift this 10 newton object. And where it makes up in terms of energy is that even when we lift up, it would take us twice as long or twice as much distance to get this object up. But that's really not the point right now. We'll get to that later. So anyway, we see now 5 newtons. So because this is pulling up on the left and pulling up on the right, the weight is split between the two objects here. Therefore, we can pull with less force. So let's do another one. Same kind of situation here. Ceiling. Object's pulling down with 10 newtons. What is the force in this wire, this wire, this wire, and this wire? So, once again, if we treat this as an object, this system as an object, the force pulling up here and the force pulling up here, we have two different wires pulling up on this one force. Therefore, the force on this one would be 5 newtons, and the force on this one would be 5 newtons. However, this 5 newtons is split between this wire and this one, so it would be 2.5 newtons here and 2.5 newtons there. So the only thing we would have to pull with a force of 2.5 newtons to lift up a 10 newton weight to get this thing moving upwards. So I'm going to go to the next page. Let's do another one. This one's going to be fun to draw. Hopefully I can pull it off. I'm going to do green. So we have a ceiling here. And we are going to have a pulley and a pulley. And then we're going to have a pulley and a pulley. And we're going to have our mass. So here we go. Wow, a big pulley system here, a big pulley system here. Okay, just to make the math a little bit, never mind, we'll keep the math the same. 10 newtons pulling down, 10 newtons pulling down. What is the force in every single wire here? What is the force in every single wire here? Well, we see that this pulley is attached to this pulley, which is attached to this mass. So we can treat all of this, because they are all attached. Oops. We can treat all of this as one system. So we have pulley, pulley, mass, but they're all moving together. Therefore, we have 1, 2, 3, 4, 5 wires. 5 wires pulling up. That means the tension in each wire is going to be 2 newtons. 2 newtons all the way across. So that seems simple enough. And to just increase the level of difficulty here, what is the tension in that wire? What is the tension in that wire? So we can treat this wire, or this whole thing, as one big system. And so if we treat this as one big system, we have this 1, 2, 3, 4 wires pulling down. We know the tension in every one of these wires is 2 newtons. If 4 of them are pulling down, that means that the tension in this one up here is going to be 8 newtons, because these 4 down here all have 2 newtons each. And if you notice, this wire, the wire up top, this wire is pulling up with a force of 8 newtons, and this one that we're pulling on over here has a force of 2 newtons going up, and oh look, 8 plus 2 equals 10 newtons, which is the exact weight of the box being pulled down. So there you go. Let's do a couple more. We're going to do red. A little bit simpler now. $10 newtons going down. What is the force in each of these wires? Well, once again, we treat this as a big system. There are 2 wires going up, therefore that each wire is 5 newtons. This problem was meant to throw you off a little bit, because this wire over here is going to the right instead of going down. This wire is going to the right instead of going down. But really, because it's a wire, because tension is constant in a wire, it doesn't matter what direction it's going. It could be going up this way, it could be going that way. It doesn't matter. That's all this was meant to do, is kind of make you think, does it really matter if it's going to the right or being pulled down? Okay, last example for the pulley problems. We have a pulley coming down, and there is a person with really long arms, apparently, and they are in a bucket, and they are trying to pull themselves down. They're trying to pull themselves down. This person weighs 100 newtons. What force must they apply to pull? They're trying to pull themselves up by pulling down. So what force must they apply on this wire right here to get themselves up? And if we treat this, because the person is holding onto this wire, we can treat this as a whole system. And so if we have a pulley, a person pulling on the wire, because the 100 newtons will be split between this one and this one, the person can pull with 50 newtons down to get their 100 newton self up. So let's go to the next page. So we're done with pulley problems. Let's go to a different thing now. There's a concept I want you to know here. And this concept is this. The further away from vertical a wire is, that's probably not very good English, but okay, oh well. The further away from vertical a wire is, the more tension. The more tension. So, what am I trying to say? We have 3 wires holding a weight of some kind. We'll say this wire, this, and this one's like this. This wire has least tension, this one has a little bit more, this one has the most, because they are further away from vertical. So let's look at why. Let's look at why. So go back. So if you put a weight on a wire like this, that wire is going to have a lot of tension in it because it is very, very far away from vertical. It is very, very far away from vertical, so it's going to have a lot of tension. This is why if you sit on a horizontal wire like this, it could break. But if you try to hang from a horizontal wire like this, it probably wouldn't break because it can take tension this way. But if you were trying to hang on to something like this, that requires a lot of tension. So let's go on to the next one. Why is this? Why is this? Well, let's take a look at a very simple example. Weight hanging from 2 wires, and they are both 45 degrees. They are the same angle hanging from the ceiling. Well, if this is pulling down with 100 newtons, what must be pulling up? The reality is 100 newtons must be going up. So that means what is going up? The vertical component of each of these is what's pulling it up. And so if this is 45 each, then that means if I did my trigonometry, because this is 50 and this is 50, because it's 100 newtons, these are equal because they're the same angle, then if I did my trigonometry, sine of 45 equals 50 over x, this being x would come out to be around 70. I could be off on that a little bit. I'm doing the math in my head right now as I go. So, if we look at a similar situation like this, and we call this wire T1 and this wire T2, notice they are now at different angles. This angle is not the same as this angle. These two things, these two tensions here, must add up to 100, but they are not necessarily equal. And I can tell you from a conceptual standpoint that this one has more tension than this one because the angle is further away from vertical. So this is just a conceptual look at wires and how they work. I strongly suggest all of you go to Khan Academy and look up Introduction to Tension. He has Introduction to Tension, and then he has Introduction to Tension 2. This will go through a math-based approach to basically what I've just done up here and here, and one more. So if you're feeling a little weak in the math area, this is where you want to be. This is what you want to be doing. I gave you a conceptual look at it. Khan is a very good math base, so I suggest you go look at his videos.